Most of us breathe ordinary air. Air contains approximately 78% nitrogen, 21% oxygen, and a small amount of other gases. At sea level, this works perfectly.
But as a diver descends deeper underwater, the pressure increases. At depths of around 30 meters or more, nitrogen begins to affect the nervous system. Divers may experience impaired judgment, euphoria, confusion, poor decision making. This condition is known as nitrogen narcosis. Divers sometimes describe it as feeling intoxicated underwater. Needless to say, becoming intoxicated hundreds of feet below the ocean surface is not a good idea.
So, what do divers do? They replace part of the nitrogen with another gas, helium. Helium is far less narcotic than nitrogen. As a result, deep sea divers often breathe a mixture known as heliox, which consists of helium and oxygen. Some divers use an even more sophisticated mixture called trimix, containing helium, oxygen, and nitrogen. These gas mixtures allow divers to descend safely to great depths. But this creates another challenge. How do we verify the composition of the gas inside a sealed cylinder? Can we determine the amount of helium without opening the tank? Surprisingly, thermodynamics says yes.
Suppose someone gives you a sealed cylinder. They tell you inside this cylinder is a mixture of hydrogen and helium. You are not allowed to open the cylinder. You cannot use a chemical test. You cannot use a mass spectrometer. The only information available to you is the pressure, the volume, the temperature, and the total mass of gas inside. Can you determine exactly how much hydrogen and helium are present in the cylinder?
Let's solve a problem from Irodov's book on general physics, which asks exactly that. So we have a vessel of volume 20 liters, contains a mixture of hydrogen and helium. The temperature is 20 degrees Celsius. The pressure is 2 atmospheres. The total mass of the mixture is 5 grams. Find the ratio of the mass of hydrogen to the mass of helium. Pause the video here and try solving it yourself. Now we try to solve this question. So we have a container whose volume is given to us. The volume is 20 liters. The temperature is given to us as 20 degrees Celsius. If we convert it to Kelvin, it becomes 293 Kelvin. This container contains hydrogen and helium. The pressure of this container, the total pressure, is 2 atmospheres. The total mass of the mixture is given to us. Is equal to 5 grams. So we know that we have to find out the ratio between the masses of hydrogen and helium. This is the question, and since total mass of the mixture is given to us, we already know that mass of hydrogen plus mass of helium is equal to 5 grams, and this is our first equation. Now, since they have already provided us with pressure, volume, temperature, and mass, it automatically suggests the ideal gas law has to be used here. So the gas law equation that we have, it is PV is equal to nRT. The pressure is equal to 2 atmospheres. The volume is 20 liters. N is the number of moles in this container. R is the universal gas constant. And its value is 0.0821 liter atmosphere mole inverse Kelvin inverse. It is also equal to 8.314 joules per mole Kelvin. And it is also equal to 1.987 calories mole inverse Kelvin inverse. But we'll be using this value because the volume that is given to us is in liters, the pressure is in atmosphere, so this value is the most suitable that we can use in this equation, and the temperature is given to us as 293 Kelvin. Now if I wanted to find out the number of moles in the container, I can use N is equal to PV divided by RT. If I substitute the values in it, I get 2, because the pressure is 2 atmospheres, the volume is 20 liters. The value of R, as I already discussed, it is 0.0821. The temperature is 293 Kelvin. And on substituting these values, I get the final answer here. This is not the final answer yet, but this is 1.66 moles. So the vessel contains 1.66 moles of gas in it. Now this includes the number of moles of hydrogen and the number of moles of helium. So number of moles of hydrogen plus number of moles of helium we have calculated as 1.66. Now number of moles of hydrogen will be equal to mass of hydrogen divided by the molecular mass of hydrogen, and number of moles of helium is equal to mass of helium in grams divided by the molecular mass of helium, and this is equal to 1.66. If I substitute the values, I get mass of hydrogen divided by the molecular mass of hydrogen, which is 2 grams per mole, and mass of helium divided by the molecular mass of helium, which is 4 grams per mole, and I get this equation. So this is the second equation. The first equation that I previously, we got the first equation here, mass of hydrogen plus mass of helium is equal to 5, and the second equation is mass of hydrogen divided by 2 plus mass of helium divided by 4, and this gives us 1.66. If we try and solve these two equations, we get mass of hydrogen is equal to 1.64 grams and mass of helium as 3.36 grams. And since the question was asking the ratio between the two masses, we get 1.64 divided by 3.36, and this gives us 0.49, which is approximately 1 by 2. And we can also play around with these numbers a little bit to become more comfortable with the idea. So the mass of hydrogen that we have calculated is equal to 1.64 grams, and mass of helium is equal to 3.36 grams. This gives the number of mole of hydrogen as 1.64 divided by 2, which is equal to 0.82 moles of hydrogen, and the number of moles of helium will be equal to 3.36 divided by 4, which is equal to 0.84 moles of helium. Now once again I'll use the ideal gas equation, PV is equal to nRT, and I can find the value of the pressure of hydrogen in the vessel and the pressure of helium in the vessel. So pressure of hydrogen in the vessel will be equal to nRT divided by V. Pressure of helium in the vessel will be equal to number of moles of helium, RT divided by V. If I put the values here, number of moles of hydrogen 0.82 times 0.0821 times 293 divided by 20. This is the pressure of hydrogen, and the pressure of helium will be equal to 0.84 times 0.0821 times 293 divided by 20. This gives us 0.986 atmospheres, and here we get the pressure of helium as 1.0091 atmospheres. Now if we add these two up, pressure of hydrogen plus pressure of helium, we get a total pressure of 2 atmospheres, which is also the pressure that was given to us at the beginning of this problem. If we go back here, the total pressure that was given to us was 2 atmospheres, and that is equal to the sum of the two pressures of hydrogen and helium. So the partial pressure of hydrogen is 0.986 atmospheres and the partial pressure of helium is 1.0091 atmospheres. And Dalton's law of partial pressure states that the total pressure P is equal to the pressure of the gases, the individual gases inside a container. So if we have a container and its total pressure is P and there are 3 gases in it, gas 1, gas 2 and gas 3, so in that case P will be equal to P1 plus P2 plus P3. And this is what the problem is about. The reason we should care about the composition of gas mixtures is because many real systems rely on precisely controlled mixtures. Industrial gas companies fill cylinders with carefully measured amounts of gases, and one method of doing that is called partial pressure blending. And in this method, if we want a cylinder containing 2 gases, first we introduce the first gas till the pressure reaches a desired value, and then the second gas is added until the total pressure reaches the final value. The beautiful idea hidden in this problem is that we can infer microscopic composition using only macroscopic measurements. Think back to how gases are actually filled into a cylinder. If we wanted to create a mixture of hydrogen and helium, we could first fill the cylinder with hydrogen up to a certain pressure, and then add helium until we reach a higher final pressure. Each gas contributes its own share to the total pressure. Without opening the cylinder, thermodynamics allows us to reverse this process. By measuring the total pressure, temperature, volume, and mass, we can work backwards to determine how much of each gas must have been added. The next time you see a gas cylinder, remember, pressure, temperature, volume, and mass may be enough to reveal its secrets.